In the last lectures, we have looked into different one particular knowledge representation scheme, namely the rule-based system. Our objective is, for this entire course, is to look into different ways in which a system can demonstrate intelligent behavior. And one of the major components of demonstrating intelligent behavior is acquiring and using knowledge. In the last lecture, we have seen one such way of representation, that is through rules. And we also concluded the lecture with one very important and popular application of such rules in the form of expert systems, which are rule-based systems. Some of the expert systems are rule-based systems. Besides rules, there are other methods and modes of representing knowledge. Today, we will start discussing on a few of those other modes of representation of knowledge. So, we will be looking at other knowledge representation formalisms, and we will be starting with our discussion on semantic nets. Now, as you must be knowing, the word semantic means meaning, all right. So, we are familiar with two words, syntax, which is essentially the grammar of a language, and semantics is the meaning of any sentence. For example, I may form the sentence correctly, which may be grammatically correct, that means it may be syntactically all right, but it must be meaningful. In order to be meaningful, it should be semantically correct. Now, when do we say a particular sentence or a particular statement to be meaningful? A sentence is meaningful when we can really understand it and map it to some of the known concepts of the real world that in which we live, or we see, we can visualize, we can realize. So, the essence of knowledge in one form is built around the concepts, the different concepts that are spread around us. Whatever we look at, for example, if I look at this room, then I will be looking at different chairs, tables, okay. Now, each of these are different concepts, and the chair, for example, is made up of wood usually. There can be chairs which are not made of wood, that may be made of iron, maybe steel or some other material. So, always whenever we talk of chair, we can think of some other associations with the material in which the chair is, by which the chair is made of. Whenever we talk of chair, another pertinent question can be, what is the size of the chair? What is the weight of the chair? All right. Whenever I use a word, say a boy, then obviously with that usage of the word boy, it certainly maps into me, it maps into a particular concept within me, because along with a boy, I have got so many other associations. A boy will be at most, if I call him a boy, will be at most of, say, 18 years old. Whenever he is more than 18 years, usually I call him a man or whatever. A boy will be having height, will be having weight, usually maybe going to school. So, there are so many other associations that come up. If I talk of tiger, then immediately some concepts, the tiger is a concept, and along with that I can associate how many legs does a tiger have. If the immediate answer is 4, okay, what is the color of the tiger? There may be two possible answers, white or yellow. So, along with, whenever we use any particular word, we are actually referring to some concept, and along with that concept we immediately associate some other related concepts. And this association of the different concepts build up our knowledge system, our conception, our knowledge base. So, this is another view of looking at knowledge, that knowledge can be represented as a network, as a connection, interconnection of different concepts. Now, in semantic nets, that is what has been explored, how we can represent a domain specific knowledge using the different concepts. In today's lecture, we will see how we can represent the concepts and how we can represent the knowledge using these concepts. And also, as it had been mentioned earlier, that I cannot call any collection of facts or information to be knowledge unless I can use it for inferring some new facts. So, if I have to call this semantic net as a knowledge representation method or scheme, then I must also have some particular inference mechanism by which I can utilize this representation to infer new things, to answer different questions. All these things we will have to look into, and that is what we will try to see in today's discussion. Now, the idea of semantic nets dates back to 1966, and through two very important papers that were written by Ross Quillian, who was one of the early workers of AI, and who tried to develop a representation of meaning. And so, this slide, as you see, has been titled as the thoughts about knowledge representation as it were in the 1960s, and also the subtitle is networks and meaning. That means that here we try to represent the different concepts in the form of a network, and also try to capture the meaning of the different concepts in a network structure. We will see how, but what Quillian tried to do is to represent different concepts as a hierarchical network. That is very important, because if I just say he is a boy or he is a man, then immediately I also know that man, yes, man is a concept, but man is a mammal, and I also know the concept mammal, and there are many properties that we share in common between man and mammals. And when I say Tom is a man and John is a man, then both these other entities, Tom and John, are also examples of man, and they share some of the properties in common because of their relationship with the common concept man. They also share, Tom and John also share some properties of the concept mammal, because all of them are connected to the concept mammal, because John and Tom are man and man is a mammal. So, in that way we will illustrate this all through our lecture today, and we can see that as a collection of different concepts organized in a network that is organized in a hierarchy or layer. Now, this model was later on amended with some psychological assumptions, because the original objective of all these exercises, all this research, was to try to understand how we, the human beings, think, how we represent our concepts in our mind. So, there has to be some correlation with the structure of human semantic memory. Not that everything is known about it, but a lot of research has gone into this aspect by the psychologists, and whatever is learned from them, that can also be utilized in our computer representation of knowledge, semantics and meaning. So, In this approach of representing meaning as networks, concepts can be represented as hierarchies of interconnected concept nodes. Okay? If I assume that one concept will be one node, say for example, animal is a concept, bird is a concept, canary is a particular type of bird, okay? Stork is another type of bird. All these are birds and they are all related to the concept bird therefore, but canary is another class of birds, okay? Sparrow is another category class of birds, but all of them share some things in common with bird, and bird again being connected to animal will have some common properties with animal. So, any concept, we can say that any concept has a number of associated attributes at a particular given level. We can say that animal, the concept animal immediately tells us that it has got skin, it eats, it runs, etc., etc., etc. All these properties are related to the concept animal. Similarly, we will have some concepts related, some attributes related to the concept bird. Now, some concept nodes are superordinates of other nodes. For example, animal is at a higher level than bird, because a bird is an animal, a tiger can be an animal, okay? A lion can be an animal, a crocodile can be an animal. So, animal is more of a superclass or superordinate of all these subclasses or subordinates like bird, tiger, etc. Again, if we go one level down the hierarchy from here, we will see that bird is again a superordinate of canary. Canary can be a bird, stork can be a bird, peacock can be a bird, ostrich can be a bird. All these are different types of birds, but all of them are birds, and all birds are animals. So, we can see clearly in this example a 3 level of hierarchy. At the top level, as we have shown, is animal. After that, there is bird. Okay? Bird is at one level lower than animal, more specific than animal. Okay? And tiger, lion, all these things may be in the same level as bird. Now, special classes of individual classes or categories of birds like canary, peacock, penguin come one level down that hierarchy. All right. So, in this example we have seen a 3 level of hierarchy, there can be multiple levels of hierarchy. All right. So, the essence of this idea is that we can organize the different concepts at different levels, and all these concepts may have some relationship from one level to another. Okay? So, that is a basic idea, and each of these concepts will have some attributes specified at that level, like animal will have some attributes, bird will have some additional attributes, etc. Now, however, we cannot store in a computer, or might be in our human mind also, we do not explicitly store everything. So, we often talk of cognitive economy. That means, how much do we store? So, for reasons of cognitive economy, subordinates inherit all the attributes of their superordinate concepts. So, what does it mean? It means that if I had specified something about bird, then those attributes will be inherited by whoever are descendants in that hierarchy. Let me give another example to make the thing clear. Say, I can say that mammal is a category. Okay? All right. So, here I can say human, and I can say might be some animals. And they are related. This is at the top level L0, this is at level L1. Now, human beings can have some attribute. I am just drawing one attribute. Let me use some other ink for that purpose. Let me use blue ink. This is an attribute link which says has, and I write down another concept, hands. All right. Now, if I draw another level down, here can be man and here can be woman. Now, man is linked to human, it is down this level L2. Now, man can have some additional properties, woman can have some additional properties over human, but whatever is there as the property of human will also be there for man or woman both. If it was not the case, say if I just go on adding properties at the human level, okay, say I say color of blood, color of blood is red. Now, if I had to store everything here, then I had to store has, hands, color of blood, red, etc. But this part is not required to be stored explicitly. I would have to store it here as well as for women and everything. So, I do not need to store this here, because this is already stored at the upper level. So, I do not need to store this part here, all right. And it is sufficient to store it at the parent level or the higher level. This is what is meant by cognitive economy. That means I do not want to store all the attributes at all the levels. Instead, whatever is there at the top level, say mammal, I can certainly say it drinks milk, all right, and or born from mother, whatever it is. Then all the children, all the concepts which are children of this level will inherit these properties that are there at the top level. Okay. So, that is the basic concept of this sentence, that is, for reasons of cognitive economy, subordinates, that means whichever are down the hierarchy, inherit all the attributes of their superordinate concepts. Now, some instances of the concepts are accepted, or there are exceptions from the attributes that help us to define the superordinates. For example, let us take one example. Say a typical classical example is that when we say bird, bird is a concept, then birds can fly. What is the locomotion of birds? Flying. How do they move? By flying. So, if I say sparrow is a type of bird, then obviously it will be automatically inferred that, well, sparrow is a bird and I know that birds can fly, so sparrows can fly. This is what we can inherit from the parent class, parent category. But ostrich is an exception. Ostrich cannot fly, but ostrich is a bird. It has got all other attributes that a bird has feathers, has wings, has 2 legs, has a beak, all those things are fine, but only the locomotion is an exception. Therefore, at the subordinate level, I may need to modify some of the attributes in special cases which are exceptions. So, the general rule we can think of that usually we inherit all the attributes of the parent, but at the lower level we can modify them in special cases as required. Various processes search these hierarchies for information. We will see how that is done. Now, here is a hierarchical network that we are talking about. Now, please look at this. What is the superordinate in this hierarchy? We have got animal. Look here where the mouse is moving, all right. This is the part where this is the superclass, I mean the top level. Now, we have got bird, we have got fish, and so these are related to this concept animal. Each of these ovals represent one concept. This oval represents bird, and look at this green link. The name of this green link or this green link is labeled with is a. What does it mean? That means bird is a animal. In proper English it should be is an animal, but we are not making a distinction here. Is a means that bird is a subordinate of this superordinate. Similarly, fish is a subordinate of this animal. Now, look at these parts. Animal, this concept animal is associated with some properties like can breathe, can eat, has skin. Okay. Now, this can and has are different attributes of this concept animal. Similarly, bird has got some additional attributes, can fly, has wings. All animals, I cannot say that animals has wings because all animals will not have wings, but bird can fly, has wings, has feathers. Similarly, if we look at this concept fish, we have got some additional attributes like can swim, has fins, has gills, etc. And fish is a animal. Now, if we go one level down the hierarchy, we will see that these colored ones are specific instances, specific, not yet instances. These are even more further specialization of birds. Canary is a bird, ostrich is a bird, salmon is a fish. Now, note a couple of things here, that if I look at this concept bird, the bird as is written over here has got these three attributes: can fly, has wings, has feathers. But just because it is a type of animal, it is a subordinate of an animal, the properties of animal are also inherited. Can breathe, can eat, has skin. So, if I or anybody asks the question, can a bird eat? The answer will be yes. Why? Because though I do not find that the attribute can eat is here in a bird, but I know that a bird is an animal, and therefore, whatever property is there in the case of an animal will also hold here. So, therefore, I can say bird can eat. Similarly, if I ask the question, can canary fly, or does canary have feathers? You see, when I described canary, I have just specified some specific attributes that are special to the category class canary. Can sing and is yellow, the color is yellow. But just looking at this, I cannot say whether canary has wings, but yet I can say that canary has wings because also know the interlink between canary, the concept canary, and the concept bird. The relationship between them is a. So, canary is a bird, and I know that bird has wings, therefore, canary has wings. Similarly, look at salmon. Salmon is a fish. and a fish can swim, has fins, has gills. So, but salmon has got some additional specific attributes, lays eggs, swims upstream, is pink, is edible, etc., etc., etc. Now, if I straightway say, does salmon lay eggs? The answer is yes, because I can see that attribute right here. But if I ask the question, can salmon swim? The answer is not here. But if I follow this link, I can see that salmon is a type of fish, is a fish, and all the fish can swim. That means all fish can swim unless specified otherwise. So, I can infer that salmon can swim. If I ask, can salmon breathe? Well, the answer is not here. I go up this link, the answer is not here as well, but the answer is here. You can see that since fish is a type, is an animal, it can breathe. But now let us look at ostrich. If I forget about, now here I have written ostrich has got the attributes runs fast, cannot fly, and is tall. Suppose this attribute cannot fly is not written over here. Suppose that. In that case, if I ask, can ostrich fly? I will first look at the answer here, and since this cannot fly is erased from here, I will look over here and I will find, well, I do not find an answer here, but let me try, because ostrich is a bird. Well, so therefore, here it is written can fly, so the attribute of bird is can fly, therefore, ostrich can fly. That would be my inference. But here in this case, we have got specific information that ostrich cannot fly. So, this attribute locomotion cannot fly, or locomotion might be walks, it does not fly, that will have overriding precedence over whatever I know from the parents. So, as I go down the hierarchy in this direction, I come from the more general to the more specific. Okay, so that's what we just now discussed, that usually we take the properties from the parents, but we go down, as we go down, there we can be more specific and we can at times override the property at a lower level. Okay, so I hope this part is clear. So, this is an example of a hierarchical network which demonstrates the different levels of hierarchy. Animal is at level, say, top level L0, bird and fish is at lower level, and canary, ostrich, salmon is at even lower level. So, here I just show what I just now discussed once again, that the same hierarchy, and here it has been shown in red that ostrich cannot fly, to show that it is an exception at the lower level. Now, there are three things that we have just now shown. The first one is called inheritance. Inheritance means any child concept will inherit all the properties of the parent concept. So, canary, ostrich, salmon will, canary, ostrich will inherit all the properties of bird, salmon will inherit all the properties of fish, and in turn bird and fish will inherit all the properties of animal. That is the first thing, it is inherited with some exceptions. Specifics can be more detailed. Think of a human species, I mean, we inherit many of the genetic characteristics from our parents. That is exactly what is happening here, the parent-child relationship. So, in general, the child inherits all the some of the properties of parents, and the child can have their own properties which were not exhibited in the parents. Similarly, here specifics can be more detailed and can be something that is inherited from the parent can be overwritten. Okay. So, this is again the same example, and it has been shown through some psychological experiments that have been carried out, that is, the tests have demonstrated that the subjects recognize when the tests were carried out on human subjects, it was evident that the human subjects recognize propositions or statements which are lower down the hierarchy much faster, much readily than the propositions which are higher up. Now, what are the propositions? Say, if I say canary can sing, that proposition is somehow stored here. How is the proposition stored? Proposition is stored in terms of the attribute and object relationship. Canary is an object having the attribute can sing. So, that is a lower, that is at this lower level. Usually, human beings first very quickly recognize the specifics. When they look at a canary, the first thing, well, a canary is yellow, a canary can sing. Oh, ostrich, it cannot fly, it runs very fast. But they think in order to state the proposition, yes, canary has wings, okay, canary can breathe. They automatically do not come in, because what you are looking, you are perceiving is at this lower level. And so, whatever is very much evident in front of you at the lower level will have more precedence, more importance. Human beings quickly recognize that. But for recognizing, not that they cannot understand the other things, they can also understand that canary can breathe, but somehow they reason, well, canary is a bird and bird is an animal, so all animals can breathe, so canary can also breathe. So, one thing is ready acknowledgement, another thing is acknowledgement through reasoning. It has been found through psychological tests that the facts which are at a lower level have got more ready acceptance to human subjects, and that justifies, that validates this model of knowledge representation. Now, we come, so till now what we are discussing is how concepts can be represented as hierarchical network. Now, we can define semantic networks. A semantic network is a structure for representing knowledge as a pattern of interconnected nodes and arcs, okay, which you must have observed by now through all the pictures. Nodes in the net, in the semantic net, represent concepts of entities, attributes, events, values, many things. Okay. Arcs in the network represent relationships that hold between concepts. Okay. So, arcs are denoting relationship. Till now we have shown only two types of, only one type of relationship, that is easy. But probably this part requires a little bit of explanation. Nodes in the net represent concepts of entities, attributes, events, values, etc. All right. So, because I can also draw a semantic net in this way, say, okay, man is a concept and man is a mammal, as I said, and man has got different attributes. I can say number of legs. I can draw another type of node 2, okay, has maybe that will be there in the mammal. So, I won't put has, I will just erase this, I will just erase this part. Say man, number of legs, I can say number of hands, etc., or number of eyes can be 2, but there can be other attributes also, like height. Now, this height can be I can say height is less than 7 feet, which is rather common. In that way, I can have different types of nodes, you see. This is one type of node that is representing a concept. There can be nodes which are representing values as well, like these are representing values. All these together are giving me some statements. Man has maybe has here, and here is a type of skin. All right. Now you see all these things are concepts. Okay. Has here, we saw that birds has feather, but man has hair. And what is here? Here is a type of skin. So here you see this is another concept. All right. This is another concept. This is another concept. And these are also, so they are different entities, and there can be also values. So it's not necessary that only concepts will be nodes. In a semantic network, we can have different types of nodes. All right. So let's go back to the definition once again. Let's see. Now, so nodes in the net represent concepts of entities, attributes, events, values, etc. We'll see events later. Arcs in the network represent relationships that hold between the concepts. Okay. Now let's proceed a little further. Now when I store this, now here I have got so many other concepts. Now when I store that in a computer, I'll store that with some particular type of coding. Now I'll label the concepts, and might be in a table I'll be storing those, I can create a table where I'll have C1, C2, etc. I'll have to encode each of those concepts, and each of those concepts can have some attributes as well. I have to store them. Now here what we are showing is that C1 is the top level concept, and I stored C1's attributes. The next level is C11, and all the child concepts are labeled as C111, C112. So C1 has got two children, C11 and C12, a sort of a subscript notation that we use. So in that particular way, we can represent all these concepts. All right. Now, where is the meaning? We are calling it semantic network. We have seen that it is a structure of nodes and arcs. The nodes are representing different concepts. Now, only the concepts by themselves, does it express the meaning? No. In order to understand the meaning of the semantics, it lies in the structure as well as the relations that are there. Okay. For example, you see the meaning will quickly change when I look at this diagram, this network, and let us compare with the earlier network. This network and has got two links, salmon, fish and animal are connected by easy links, and I just change at this level these two links from easy to eat. You see the structure, if I just withdraw these labels, the other structure, the concepts and their linkages are remaining the same, but only thing that I have changed is the relation. Now immediately the meanings have changed. Now what this structure means is salmon eats fish and fish eat animals. Now I can no longer say, answer questions which I was being able to do earlier. Okay. Does salmon have fins? Well, I look here, salmon lays eggs, salmon swims upstream, salmon is pink, salmon is edible, and well, I do not know whether it has fins or not. And because I cannot now recognize that, well, salmon is a fish, that link, that connection is lost. If I had another link over here, easy link, then it would be all right. I could have traversed through that easy link and could have arrived at that answer that salmon has fins. But as the structure lies now, well, I can only say salmon eats something called fish which has fins, but whether salmon has fins or not, I do not know. In fact, it has become a really meaningless thing that fish eat animal. Is not always the case, but you see how by changing the relations the total meaning changes, and whatever I was being able to do earlier in this case, I cannot do any further because of the missing link here. All right. So, the important thing to state is that whether we can represent the meanings and the concepts in the form of semantic networks. Yes, the answer is yes, we can do it, but the meaning lies in the structure as well as the labels of the arcs, that is what are the relations that we are giving. Now, we are talking of concepts. We have just mentioned of propositions. Salmon eats fish, that is a proposition. Ostrich cannot fly, that is a proposition. If you recall, we had encountered proposition earlier when we were discussing logic. So, is there a relationship, or are they absolutely two different things? Can we represent whatever we are stating in semantic nets through logic, and whatever we are stating through logical propositions, can they be represented in semantic nets? That is a very natural question. So, let us look at this example. Suppose this semantic net where we have got 4 concept nodes. Person is a mammal, person has spot head, and Tom is a person. Now, here you see Tom is a specific person. All right. So, till now person is a category or class. Those of you who are familiar with object oriented systems, the concepts of objects, the classes, subclasses, will find a similarity here with the concept nodes that we are discussing. But let me state here that the concepts of objects and object based design, object oriented systems came much later and has been systematized much later. These network concept of representation of meaning dates back to 1960s, as we have said, and so this is a predecessor, and it has been certainly much systematized later, but nevertheless here if we had talked about object oriented terminology, then Tom is an instance of the class person. But person could have, say if I had added a node here, man is a person, woman is a person, then man, woman are still classes. I am not talking of a particular man or a particular woman, but Tom is a particular person, and through these easy links in semantic nets I am not being able to, in general through this easy link I cannot make this distinction between whether it is an instance or a class. However, that we will discuss much later. Here you see that Tom is a person, person is a mammal, and person has spot head. So, if we just look at this part, okay, I can answer some questions. Does Tom have a head? Yes, I can answer Tom is a person and person has spot head. Yes, so Tom has head. And whatever were the attributes of mammal, I could also talked about those attributes to be valid for Tom. Now, the same structure can be represented in logic where I just use these relations as the predicates. Is a person mammal, is a person mammal. So, it is a binary predicate with 2 attributes, right. Now, in logic I can say instance Tom person, the Tom is an instance of a person, has spot person head. So, you see each of these partitions, any 2 if we take and take the relation connecting them, I can represent them as propositions as we do in logic. Now, if we now let us pause for a second and revise what we have just now discussed. We started with the point that we want to represent concepts and the meaning, because that is essential to represent knowledge, and we have seen that concepts can be stored or represented in the form of a hierarchical network, and using this idea, the semantic net representation came into being, where the nodes it consists of nodes and arcs, and the nodes represent concepts, entities, events, values, and the arcs represent different attributes. Okay? That is how we can represent different facts that we want to state about the real world that we want to model. Now, let us see how we can represent some more facts in semantic nets. Suppose there is a game being played between two teams, all right, Norwich and Spars. Now, one team is a winner, another team is a loser. Now, how do you represent that fact that Norwich defeated Spars? Say I just want to say Norwich was the winner and Spars is the loser. Then what I need to do, that Norwich is a winner, winner of what? So, winner of a particular game which I have just named here G5, and what is G5? G5 is a game, and any game will have a winner and a loser. So, Norwich is the winner and Spars is the loser. All right. Now, if I want to state that, if I want to state that Norwich defeated Spars with a score, and it was a football match, the score 3-1, then I have to add another attribute score 3-1. So, in that way, let us forget about what is written below, these yellow lines, let us forget. Let us first look at this white thing. Now, what can we say about this? We can say that, well, G5 is a game that was played in that some particular ground. I could have even stated those. G5 played at, I could have added a particular arc over here saying that it was played at some particular ground, football ground. And the attribute G5 is a game, and it has got a winner and loser. So, if I look at, I can say that in the game G5, Norwich was the winner and Spars was the loser. And if I look at this, I can also say that the result of this game G5 was 3-1. Now, typically earlier what we have seen is when we take these two nodes and look at the relation between them, what we represent is a two-place predicate. A predicate is a which can take two parameters, all right. But often we may need to represent facts with more than two parameters. For example, Norwich defeated Spars with a score 3-1, or the score of Norwich over Spars was 3-1. Now, these are three-place predicate. Now, how do you do this? In order to do this, if I had just taken these two, what would I have said? Spars was the loser in game G5. If I had just taken these two, what would I have said? I would have said Norwich was the winner in game G5. If I had said what is G5, I would have looked into these two nodes and would have said G5 is a game. If I had taken these two, I would have said that what was the score of G5? The score of G5 was 3-1. All these were two-place predicates. But whenever we need to represent three-place predicates, I need to create a new node. Okay, this new node had to be created, you see. Otherwise, I could have just said game. In this game, there is a winner and a loser. I could have said Spars and this. But the score of different games will differ. So, I may need to create a particular node which will specify the additional fact. We will see some more examples from here. For example, if we look at this point, we see that it is a more complicated example which we are trying to show. John gave Mary the book. John gave the book to Mary. Now, how do we represent this? We have shown that gave is an action, there is an event there is a this giving the book to Mary is a particular event, and this event of giving has got an agent, somebody who gives and somebody who receives. Any giving will have two requirements, somebody will have to give and somebody will have to receive. Who is giving? The person who is giving is an agent, and the person who is receiving is the recipient. So, this event, which is an event of giving, the action is giving, has an agent John and a recipient Mary. Now, what is being given? The object that is being given is a book. What is that? A particular book. John gave Mary, you see, I am not saying John gave Mary a book, I am saying John gave Mary the book. So, I am talking of a particular book. So, I can say John gave Mary, this event has, this giving event has got an object. I can give you the pen, I can give you the money. So, giving is an action which has got a giver, which has got a recipient, and also some object that is being given. Okay, there may be more objects, how it is being given, all right, when it is being given. I am not going into those because those are not required by this sentence. John gave Mary the book. So, the object that is being given, I could have said book, but why didn't I say it is book? Because book is a general class, and we are talking of a particular book, that is book 69. And what is this book 69? It is an instance of book. So, you see how this English statement John gave Mary the book simply translates to this nice semantic net form. Now, here we have got all these are entities, event, John, Mary, book 69, book is a class, giving is a class, these are concepts, concept of giving. I could have written over here giving also, but this particular node is gave because its tense is past, which is a type of giving where the tense is past, etc. I can make it more detailed. So, this is one example. So, we will just conclude today by giving another example, and we will proceed from this point onwards in the next lecture to show how the inferences are done, but let us first look at another example. Suppose we are asked to build a semantic net that represents the following knowledge. We have just now shown that given a particular semantic net, how that can be represented in the form of logic. Now, what we are showing in this example is given some logical statements, can we draw a semantic net with that? So, let us look at these statements. Man Marcus, that means Marcus is a man. Married Marcus Madonna. So, Marcus is married to Madonna. So, these are, you see, propositions. Gave to Madonna Marcus measles. That means Marcus was infected by the disease measles because Madonna had it. So, Marcus got it from Madonna, all right. So, this infection we are explaining through this. Gave to Madonna, Madonna gave to Marcus measles. So, you see these are three place predicate. So, these three statements, so it is a story. Marcus is a man, Marcus married Madonna, and you know what happened? Marcus was infected with measles by Madonna. Now, how do I represent this story in this form of semantic net? You see here, Marcus is an instance of man. So, I take this sentence, man Marcus. Marcus is an instance of man, which is a concept. Madonna is another instance. Marcus is married to Madonna. So, you see the second statement is also covered. And third thing is giving. Now, Marcus and Madonna married, and they probably gave so many gifts to each other, maybe so many other things were there, but this giving measles is a particular instance of giving. So, I cannot directly relate it to the concept giving, it is a particular giving. So, therefore, I can denote it with a particular giving. G17 is an instance of give action. Okay. Madonna also gave a book to Marcus. All right. So, I cannot just say it is all the give actions are connected to this. This is a particular give action. Now, this particular give action has got the what was given thing is measles. Of course, measles is a disease, but here we are simplifying it. So, the thing is measles. And who gave? Whenever there is a giving, who gave? Madonna gave, and who got? Marcus got. So, you see, now I can look at the earlier presentation here and I can understand many things from these theological statements, and the same thing I can understand from this semantic net structure that I show over here. So, today we stop at this point, and in the next lecture we will start from this point onwards, and we will see some more representations of semantic nets, how semantic nets can be used to represent more complex concepts, and how we can infer using semantic nets, and that will be followed by other knowledge representation schemes. So, we stop here today.